This lecture is going to cover sections 8 and 9 of Chapter 6, which is on the VSEPR theory and shapes of molecules and polarity of molecules. Section 8 is shapes of molecules, and we can obtain or guess at the shape of a molecule by using what's called the VSEPR theory, which is short for valence shell electron pair repulsion. This theory describes how to determine the generalized shape of simple molecules or the generalized shape around a centralized atom within a large molecule. It takes into consideration the electron-electron repulsions of valence shell electrons from neighboring atoms within a molecule. Since electrons will repel each other, these pairs of electrons will assume positions as spread out from each other as possible in order to be as low in energy as possible. So the electrons in molecules don't like each other. They want to spread out and be as far away from each other as possible. So this concept dictates where the electrons can be when one set is bonded to one atom and the second set is bonded to a second atom, and so on and so forth. So firstly, we have two groups of electrons around an atom, a centralized atom, and an example would be carbon dioxide. Now, if we look closely at carbon dioxide, we have a double bond here and a double bond there. So there's two double bonds. The carbon atom, therefore, has a total of 4 bonds, which is what you should expect it to have. So that's good. But it only has, and this is the key, it only has electrons coming off in 2 directions. So those 2 directions have to be as far away from each other as possible, which is 180 degrees. So you see this bond angle there is 180 degrees. The electrons of the bond on the left, right here, are 180 degrees away from the electrons in the bond on the right. Anytime that an atom, whether it's carbon, nitrogen, sulfur, anything, has only 2 what I call sets of electrons, meaning electrons only come off of that atom in 2 different directions, it has to be 180 degrees, no matter what. Now notice we have a name for this, and it's a linear electron group geometry. Other times it's called linear triatomic because there are 3 atoms here in CO2 and they're in a linear arrangement. If we have 3 groups of electrons around an atom and there are no lone pairs on that atom, so this carbon atom has no lone pairs, we have these 3 different sets of electrons. We got the double bond to the oxygen, we have a single bond to one of the hydrogens, and a single bond to one of the others. You might draw it that way, but in reality, if we look at the angles between these, let me zoom in a little bit. The angles are going to be 90 degrees, 90 degrees, and 180 degrees. So they're all different. It lacks symmetry, and this is why this is not the shape of this molecule, which is formaldehyde. Let me get it there. All right. So you can see the picture to the right of that, right here. This is 120 degrees. This is 120 degrees. And this is 120 degrees. We have symmetry here, and that's the key thing. Symmetry is always what we're looking for. The name of this shape, when there's 3 groups of electrons, when there's not a lone pair on that centralized atom, is called trigonal planar. It is a flat molecule, and it has 120 degree bond angles. If there are 3 groups of electrons around a centralized atom and there's 1 lone pair, we get what we call a bent shape. And so you can see the lone pair of electrons is on the sulfur right there. How I would draw this would be like this. So I have sulfur, here's a double bond to the oxygen. It doesn't really matter which oxygen gets the single or the double, but you still have a lone pair in that sulfur, and it's going to be like that. And so you still get 120 degrees around each of these. It's actually 119 for SO2, but that's close enough to 120 that it doesn't really matter. So it assumes this trigonal planar shape. But I should say geometry. But we don't include the lone pairs in the shape, in the overall shape of the molecule for some reason. So what you get are just the 3 atoms, and you can see in the picture right here, we've got those atoms, and we've got these right there, those 2 bonds, I should say, and they're 120 degrees away from each other, so it is bent, or more commonly, bent triatomic. 3 atoms. If there are 4 groups of electrons around an atom and there are no lone pairs, we get what's called a tetrahedron, or a tetrahedral shape. Tetra means 4, hedra means faces, and you can actually see it in here. The faces, it's hard to actually see the line, but there's a line right there. This is a prism with 4 faces. Here's the front face on the left, front face on the right. There's a back face all the way around there, and then there's a bottom face right there. Let me get back to where we were. All right, so we have this. It's called tetrahedron when you have 4 groups of electrons around an atom. And the reason that is because if you look at this, there's a 90-degree angle here, 90-degree angle there, 90-degree angle here, 90-degree angle there. And that looks really symmetrical. But what we also have to look at is the bond angle between these 2 hydrogens, which is 180 degrees, and these 2 hydrogens, which is also 180 degrees. So 3-dimensionally not symmetrical. What we're looking for is symmetry in all 3 dimensions, and the tetrahedron gives you that. Now it's hard to see in this 2-dimensional plane you're looking at a picture that's trying to look 3-dimensional, but all of the angles are 109.5 degrees. So you have right here 109.5 degrees. You've got between these two 109.5 degrees, between those two 109.5 degrees, between these two 109.5 degrees, but you also have this hydrogen to that hydrogen being 109.5 degrees, and you have this hydrogen to that hydrogen is 109.5 degrees. So this one is symmetrical in 3 dimensions. And what you can key in on here is the angle, 109.5. That is bigger than the 90s. The more spread out, the better. All right, so when you have 4 groups of electrons around an atom and there's 1 lone pair, we get what we call a trigonal pyramidal shape. And so that's right here. So the atom assumes a tetrahedral geometry. But again, we don't include the electrons in the lone pairs, so we only look at the 3 atoms that are bonded to the central atom. And you can see from this picture here, the central atom is above the plane of the bonded atoms. And so it forms this pyramid. Not the pyramid because of that lone pair, but you just form this pyramid that has a 3-membered base. Like that. You'd have a nitrogen at the top of it. Whoops. Nitrogen up there, and then you'd have the hydrogens right there. All right, so we call that a trigonal pyramidal. Now, keep in mind, this applies to any set of atoms. When there's 1 lone pair and 3 atoms bonded to it, it will always be trigonal pyramidal. If there are 4 groups of electrons around an atom and there are 2 lone pairs, we get what we call a bent triatomic again. Water is a good example of this. The oxygen has 2 lone pairs on it. If we look here, we have a 90-degree angle. In reality, the angle is close to 116 degrees, I believe, which is bigger than 90, so that's good. And so you get this bent shape. But it too assumes a tetrahedral geometry. Okay. The reason that the bond angle is slightly different, I'm sorry, not 116. I'm thinking of something else, obviously. It's about 106 degrees. Good thing I kept talking. So we have 106 degrees, and the reason is that it's not 109.5 is that the lone pairs on these electrons are allowed to take up much more space. So if I was to delete all this, let's move this to the side here. If I draw water, we have oxygen, we have a hydrogen here, hydrogen there. We've got a lone pair here, and a lone pair right there. This is called a dash, and this is called a wedge. The wedge is in front of the board, and the dash is behind. Weird. The other two are in the plane. All right, so we have that. The bond angles are 109.5. Now, just to explain that, if I draw it again in a different orientation, I can put the dashes and the wedges up here. It doesn't really matter. But if we look at electron clouds around these lone pairs, they're going to actually be allowed to take up a whole bunch of space. And that's because the electrons are not tethered, in a sense, between two atoms. In the electron clouds that have, for the rest, we have the hydrogen's going to be like this. And for the other one, we've got right there. Since these electron clouds are so big, they actually push these two hydrogen atoms together. So the bond angle gets a little smaller.